Hey guys, this contest, Codeforces Raif round 1, I think. This was absolutely insane. I started off with like a pretty decent A, fine, and then B I took 11 minutes on, which was like a very bad time. By then 900 people had solved it. And then C I took another 12 minutes on and by then, like, I'm sure like 1,000 people or so had solved it. So I was starting off the contest with a very, very bad penalty. And, well, it kind of, D took a very long time too, longer than it should have, so it just got worse from there. And then E was fine. E I got quickly because it was something I had seen before, so it's kind of fair. And F, I failed the sample for a very stupid reason. And so that gave me a penalty. And then it took me longer than I should have for F2. So that's unfortunate. But then, when you see the standings, it turns out that if you look at the top, a lot of the people at the top have hacks, specifically on B. So I tried to do this too. And as it turns out, I got 3 hacks, which was enough to give me a predicted delta for IGM, which is insane. And if I don't fail system tests, it's happening. So that, I don't know, that's kind of crazy. I felt so hopeless when I wasn't able to solve G, but then I just looked at my room and it turns out 3 people's solutions were wrong. And I do feel kind of bad about it because someone did actually lock their problem, and so they weren't able to resubmit, but what can you do? That's part of the game. So, yeah. Okay, anyway, this is a solutions video, not a rambling video, so let's do solutions. And meanwhile, I'm going to be anxiously checking for system tests, because I feel like B, C, and D are kind of sketchy. E and F I'm confident about, and A is like A, so I would hope it's fine. Okay, that being said, let's do solutions. So A is basically you have a box, and you have like a what is it? A wabbit. Okay, so you have a wabbit, and like in one move you can like pull both the box and yourself in some direction, provided that you're like at that direction from the box. So like if you're right below the box and you have to be right below, you can't be like super far below, then you can pull both the box and yourself 1 unit in 1 second. Yeah. And you can also move 1 unit in 1 second. And you want to figure out, given some starting location, what's the minimum amount of time it takes to get to some ending location. Where you can start, you as the person can start wherever you want, but the box is fixed. Kind of confusing this in Wabbit, but whatever. Okay, so basically, consider the X and Y directions separately. Either you have to pull to the left, you have to pull to the right, or you have to pull like neither. You're already on the right X location. So if you have to pull to the left, then there's no reason to ever try and go to the right, because that's just going to hinder your progress. And similarly, if you have to go to the right, then there's no reason to go to the left. So therefore, there's only one direction you have to go in the X direction. And specifically, it's kind of like the displacement, the absolute difference between the coordinates, let's call it dx, equals absolute, like the box is x minus the final x, or the starting x minus the ending x. And we can do the same thing for dy. Let's compute a value dy equals the absolute value of the starting y and the ending y. Now, say one of these values is 0, or both of them. Then you only have to pull in one direction, specifically this one. So you can start at the point where you're already able to pull, and then you don't have to spend any extra time moving around the box. And same for y. But if you have to go into both directions, say you're here, and then the final path will be something like this, you can start in one direction, say here, pull it down, but then you have to spend an extra 2 to move around to the other side so you can pull in that direction, or possibly over here. Actually, sorry, you would be below the box, so you would come from here or from here. So basically, like, compute these values, dx and dy, and then if at least one is 0, which is the same as the minimum of the two is 0, then it's just dx plus dy, because you only have to pull in one direction, and the total seconds is going to be the number of units you have to pull. Otherwise, you have to spend an extra 2 walking around, so it's just simply 2 plus dx plus dy. And that's essentially the answer. You compute these absolute differences between the coordinates. If the minimum is 0, then it's just the amount you have to pull. Otherwise, you have to spend an extra 2. Have system tests started yet? That's scary. Okay, so B, I'm going to do my idea. I haven't verified that it's correct yet because system test, but I believe in it. And my hack didn't work on me, so I hope it's right. Nope, sorry, this is B, not C. Not the problem C. I did not say that word intentionally. Very scared about this. What happened? Did it just say accepted and then jumped to in queue? Seriously? Okay, well, so here's the idea. You have some conveyor belt, and you have 3 types of things. You have some, like, actually you have a circular conveyor belt. I'm just going to assume it's circular. And then so you can jump from here to here, for example. So, I mean, you can, I guess I'll draw it in a circle. Why not? Can't really hurt. So you have some circular conveyor belt where, God, this is not going to work. I don't know how to draw this. Does this look fine? I don't know. It's kind of fine. It's fine enough, I guess. And basically, you want to figure out, and so in this conveyor belt, say you're at some point. If either you have a line or, like, consider the left. If it's, okay, this is not working. So each, like, you have a bunch of points, and every, like, segment in between the point either has a direction or doesn't. If it doesn't, you can move between both of these. If it does, you can only move in the direction which, like, the direction signifies. You can't go this way, which means I drew it in green to say you can't go that way, because that's how colors work. And, yeah. And similarly for here, you can't go this way. You can only go in the direction that the conveyor says you can. So basically, you want to figure out how many points are there so that when you start here, move at least once. When you start here and move at least once, you can eventually end up back at this point. Okay, and this is kind of, if I did this right, it's kind of a casework problem. That's testing. Okay, if I did this right, it's kind of a casework problem. Don't fail. Don't fail. I believe in you. Don't fail. Don't fail. Oh, it's actually taking some time. Why are there so many tests for this? It's multi-test, isn't it? Nice. Okay. Awesome. That was one of the ones I was scared about. B, C, and D again. So let's consider some position. Say here. Then, like, what's going to happen at this position? Say you have some, like, undirected place to the left or right of it, just, like, adjacent to it. Then you can go from here to here and then immediately go back. So instantly, like, this is reachable. If any point has a segment to the, like, it's adjacent to some undirected segment, then you can immediately conclude that it's reachable. Otherwise, it doesn't, and therefore the segments to the left and right of it are both directed. So say you have something like this. Then you can easily leave this point, but how are you ever going to get back? Because you can't go this way. I'm going to draw it in green again. You can't go this way, and you can't do this. There's no way you'll ever come back to this point. And in the same manner, if you have something like this, you can't even leave. Like, there's just no way to get out. So if the two things to the side are not equal, then immediately it's not possible. And if the two things are equal, then we're kind of interested in what condition can we get back to this? Well, this is like a circle, right? We got some circle here. So we have to be able to, first we have to move here. And then we can't go back here. So we have to just keep going right until we eventually get to the end of the circle. These arrows are terrible. But eventually we have to keep going right until we get to the end of this circle. But like, just look at this. Like, this path goes around the entire circle and visits everything. So if we can do this, that means every node is reachable. Or whatever, that was the word they used, right? Or returnable, sorry. Every node is returnable. You can start there and go back to it, because you can just take whatever this path is. And it's the same thing if they face the other way. But otherwise, if you can't do this, then you can never get back, because you can't come from the left, and you obviously can't come from the right. Okay, that being said, how do we check if something is reachable? Well, we can pick some node. And then if there's a cycle that traverses the full circle, then we can just say, let's just go to the right until we can't anymore, or until we hit the node again. And using that, we can just see immediately if there's some path that can visit the circle. And the same thing kind of for the left, that if you can go to the left, then it just like, it's fine. But it's not enough, and this is actually where my hacks came from, it's not enough to just check if there's some point where the two adjacent conveyors aren't equal. Because say you have something like this. What did I do? It was this. You have this, and then this, and then this, and then this. And then we'll just assume this is like an arrow. Right, so clearly if you go here, then you're like stuck within these two. And if you go here, then you're stuck within these two. But there's no path that like traverses the whole circle. And even though like all of these are reachable, it's very easy to construct a case where all of them aren't reachable. Let's just do something like this. And right now this cell specifically has it doesn't have any like undirected things to the left or right of it, but it is like, it's deceptively possible to make this because there's no cell where the two conveyors adjacent to it are different. But clearly it's not possible because it's basically equivalent to the conveyor with 4 we had before. So just checking this doesn't work. What you can either do is you can just explicitly check if there's a cycle, or you can say, like, look at this. If you have like something like this, right? You have a bunch of these and then you have a bunch of these. Then you can always keep moving right. At any point you can move right. But if you have something like this, then there exists a point where you can't move right. And therefore there's no cycle where you can keep moving right because there's a point where you can't move right. And it kind of goes the same for the left. If there's any of these, then there's a point where you can't move left. So what that boils down to is if you have at least one of both of them, of like the directed ones, then it's impossible. Otherwise it's going to be possible because at every point you can move right. So like this is kind of the final condition. If you have any of these, if you have both of these, then there's no cycle, and therefore the answer is the number of points that are adjacent to some undirected segment, say the line. And otherwise, then there is a cycle, and the answer is n, because every node can go from the cycle and like eventually get to itself again. That is the idea. Do we pass system tests? We got C. Okay. All right, that's good. This is so scary. I'm scared about D still, because I don't know, it feels like it's kind of caseworky, kinda. Well, I'm not sure. Okay, so whatever. What can we do now? This is C. It is titled ABBB and doesn't have any C's in it, which is kind of disappointing, but whatever. So we have a string. Let's say we have the string that they give us. Jeez, what the hell? We have. All right, writing is going well. A B. Is that what they have? Yeah. A B B A. Okay, and the plan is, or no, what am I saying? In one operation, you can remove a substring. You can remove a substring of two characters that's either AB or BB. You can't remove BA or AA. So in one operation, you can remove one of these two, and you want to find out what's the minimum length of string. Like the minimum length of the final string that that you can get by doing these operations. Now let's look at this. Both of these like removals have a B on the right of it. I'm gonna move this over. Also, this is kind of messy. So both of these removals have a B on the right, which means that it's going to be some B and then something else, either A or B. So let's kind of like consider the string again, I guess. The idea is we'll go backwards through the string. So let's go this way. And we ask if we have an A, or say we have some B, then like it's better, if possible, to use this B to remove an A instead of another B. Because if we use these two B's to remove each other, then it's possible that we don't have another B to get rid of any A's to the left of it. But if we first use the B's to get rid of all the A's that we can, then it's going to be better. Because then we can later on, now that we've gotten rid of as many A's as we can, now we can merge as many B's as possible. And that works because, so basically the idea is we iterate backwards through the string. Whenever we have a B, we look for any A. And we can do this kind of with 2 pointers, where once we have a B here, we have a pointer to the next A. And then when we remove an A, we can move the pointer over to the next A. And since both pointers only move left, it's O then. And say this pointer is here, and we're at this place, and we haven't removed this A yet, then we just kind of like force ourselves to move the pointer over to the next A because there's nothing we can do with this A. So the basic idea is 2 pointers, where you have one pointer to the A and the other pointer to the thing you're like iterating towards. And if you have a B, then you first try and make it so you can remove one of the A's. And if you can't, if the pointer is at the beginning of the array and it has no more A's to point to, then and only then can you use the B's together. But like, think about what this string is going to look like, right? You have some B's and then there's no A's to the right of them. So the final string, once you finish the 2 pointers and don't remove the contiguous groups of B's yet, is going to be like this. It's going to be like it's going to be like all B's on the right end and then all A's on the left end. And note that these A's being here means that there's no B to the right of them that was able to remove this. Oh, and by the way, we can treat, even though this isn't a substring, like we can basically say it is, because if this is here and this A is here, then there's going to be like some B in between that we can use instead of this one. But because these are kind of together, these B's are kind of equivalent. So it's okay to say that this and this are removed together, because it's equivalent to saying that the one adjacent to it and this A is removed together. So that part's fine. Right, okay, so we have these A's, and from here so these A's, no matter what we did, they couldn't have been removed. So these A's are immediately have to be part of the final answer. And then these B's, well, these are all the B's that haven't been used to remove A's in the string. But we removed as many A's as possible, and now we're going to end up with at most one B in the end of it. Because all the B's are going to end up like this. And you can kind of work out the casework if you want to show that the string is going to look like this eventually. So once we get to this point, we can just remove all the remaining B's we have. And yeah, that's basically it. Because we remove as many A's as possible, and at the same time we remove as many B's as possible without the conflicting of greedy. And so it's just going to be correct. Okay. Yeah, basically 2 pointers. All right, this is the moment of truth right now. Did my D pass? Oh my god, that's a lot of tests. It's always testing right when I get to it. Oh yes, we got the tag. We got it! Oh my god. Sorry for noise, but okay. The reason I'm happy now and not later is because I'm very sure that E and F are gonna pass. I hope at least. Because they're not even close to the time limit. I think my algorithm is correct. It's kind of maybe my E won't actually, but okay, this is where the problems get kind of interesting. So, actually no, the other problems were fine. They were just, this is where they get hard, I guess, from my view. Because this one took me what was it, 30 minutes to, no, my submissions. Yeah, it took me 29 minutes to do, basically 30. Alright, so, this is going to be fun to visualize. Might just copy this in and go from there. Hopefully that didn't glitch the visuals. So basically, here's how this works. You have a grid, and then you're going to throw some boomerangs or whatever at this grid. And so from each column, you'll throw a boomerang. And then this boomerang is going to go up and up and up until it either gets to the end or it hits one of these X's. And once it does, it's going to turn to the right, basically. Clockwise, is that? I think clockwise? I don't know. But you're going to turn to the right, and then the boomerang is going to go in this direction until it either hits the end or it hits another X, and then it's going to turn to the right again, just like this blue path goes. And so, for example, if you throw it here, it's going to hit no X's. And if you throw it here, it's going to take the red path. If you throw it here, no X's. If you throw it here, it's going to hit this, and then it's going to go to the end. And then when you throw it here, it's that. And so what you're interested in kind of is the number of times the number of X's each boomerang hits when it gets thrown in a specific column. And you know this is at most 3 because there's no way that it can be more than 3 because if there is, then actually no, never mind. There definitely is. I'm confused, but basically okay, that's just the problem. They give you the constraint that each boomerang hits at most 3 different targets between 0 and 3. So this is where the problem is not trivial. You are given the times each boomerang hits an X, and you want to construct the grid. You want to find where the X's are. So it may not be possible. In that case, just print that it's impossible. And there's an extra constraint. Each row in each column can have at most 2 X's, which ends up mattering. So first what I want to do is just check. We got E. We got E. All right. Just need to get F now. I don't know why F would fail, because it's like very, very straightforward in a sense once you get the solution. And it had 20 pretests, I'm pretty sure. So that's a good thing. Okay, so this also kind of comes down to casework. This problem D we have here. Let's draw a poorly designed grid because I'm doing this with a mouse, and sorry for the OCD people. Might have OCD myself. Okay, right? So, and then we're going to use the sample. Let's say this column boomerang hits 2, this hits 0, this hits 3, this hits 0, this hits 1, and this hits 1. Okay. Now consider what happens. Obviously there has to be an X in this row. Or in this column, right? So let's just like put it anywhere. Let's say we put this here. And then there has to be some other X to the right of it. So what happens here, right? If we have some X here, say for example in this place where there's a 3, what did I just do? How did that, what? Why am I not able to undo that? So we have some X here, and then basically we have to have some other X to the right of it. So we're gonna say we put this X in the column where there's a 3. But then we have to have another X to the right of this, because this has to hit something else on this path. So if we put some X somewhere else, then we're gonna have 3 in this row, and that's not allowed. Yeah, I guess otherwise it would be very easy to solve, actually, I think. Yeah, it would definitely be way easier to solve if there wasn't the constraint of 2. Right? So we can't put this extra X anywhere where there's a 3. And we also can't put the extra X anywhere where there's a 0, because, like, just duh. Like, there can't be any X in that column. And by the same argument, we can't put it where there's another 2. Let's say this was a 2, and we put the X here, then we would have to have another X to the right of this, but we can't. So the only place where we can put the X for the 2's is out where there's a 1. And specifically, it has to be on the same row. So we can kind of do this in a greedy manner, and we'll elaborate on why this works later, but we can just take the closest one to the right of it. And this can be done, again, with another type of 2 pointers, where basically you maintain a pointer, and this represents, like, wherever you are, this represents the closest unused one, because if you already used the 1, you can't use it again, otherwise there'd be multiple things in the column, and then this path would go down and hit 3, and that's not allowed. So this pointer represents the closest unused one to the right of I. And so when you use a 1, or when I moves over to here, you would move the pointer to the next one, and then when the pointer's at the end, you wouldn't have any more 1s. So that's a case where it's impossible, if you don't have any more 1s, but you need 1. Okay, but okay, now we've kind of solved 2's. Basically, we just need to find any 1 to the right of it, and then just say, like, we're going to put somewhere else there. Right, so actually this is what the grid would look like. And then now we have the constraint that, like, this 1, its row is kind of fixed. We have to, because of this 2, we have to put this on row 1. Because if we don't, then this X wouldn't be here, it would be somewhere else, and that just wouldn't work. So when we have this 2, we can essentially say that wherever we put the other X, the row where we put the X on is fixed. Okay, now let's look at 3's. So this row is taken, so we have to put this on a different row. Let's go here. And once we do that, and we can just assign the rows, like, greedily from top to bottom, it's just going to work out. So once we put this here, actually wait, I want to check. Has my F passed? It does. We got it. We got everything. Wow. This is IGM right here. Jeez. It's just, like, happened so fast. Like, I was read 2 months ago, and now we're just totally blasting through. Maybe 3 months ago, but jeez. It's, like, insane. It's what is it? Like hyperbola maybe more of a hyperbola, but it's gonna kind of like get steeper here. Wow, that's so crazy. Yeah, that is crazy for sure. So I'm going to be making a special video. As I said in my about section, there will be a special video for reaching IGM because why not? What happened? This should be higher. This should definitely be higher. Right? It should be higher. Is predictor going to update? Okay, there we go. Wow. This is insane. It just simply is insane. Okay, let's get back to this. So we have a 3 here. And so therefore we need to have some other x to the right of this. So again, we can't put it in 0. But this time we can put it in other places. Let's draw some like virtual rows or something, right? So let's say we have a 0 over here, a 1 over here, a 2 over here, and a 3 over here. Obviously we can't have 0, because if we do it, the 0 is going to hit it and it won't be a 0. If we have a 1, then this is kind of like allowed to roam freely. Actually, if we have a 1, right? So this is going to hit like this, and then it's going to hit like this, and then it's going to go down. So then that implies that we put a different x, say the row directly below where we put this x. And so we don't have the same constraint that we do with 2, because now this is on its own row and we only have one of these. So if we have a 1, we can do it like this. And this row is also taken because now we can't have anything to the right of this, otherwise this 1 would hit more than 1. If we have, say, a 2, let's move this over here, then we still have this right below it. But that's fine because now we're allowed to have something else to the right of it, because this is on its own row. It's not the same row as before, so we only have one of these. And similarly, now we fix the row of the 2 to be row 3 because like we already mandated that this has to be here. And in the same manner, like we can do the same thing with 3. What? We can do the same thing with 3. This will just go down here, and then we'll have something else going on to the right of this eventually. But that doesn't matter, all we care about is this one. So 3 can accept basically any 1, 2, or 3. So we can kind of have a different pointer that represents the closest point after I that's either 1, 2, or 3 and hasn't been used. And we can also use the fact that like these rows are either fixed or they aren't. So we can say something like a row is -1 is that if it hasn't been fixed yet. And then it's only been used when its row is not -1, because then its row is fixed by some previous thing. So we basically kind of match 2's to any 1 to the right of it, and match 3's to any 1, 2, or 3 to the right of it. Now 0's obviously don't match with anything, and 1's can't match with anything because there has to be strictly nothing in this row. And so this row is taken. So for 0's, we do nothing. For 1's, we just assign it an extra row and then move, and then however you're keeping track of rows, just like get rid of that row because you can't use it anymore. And once you have that idea, it's just constructing the answer. So yeah, another kind of 2-pointers problem. That was D. Okay, let's finish this off. Check the standings again, because it can't hurt. We're definitely going to go down as more people solve G, but like definitely it's enough for IGM, for sure. What the hell? So you just like solve everything? Okay, alts, nice. So we do it. Alright, here we have some carets. Let's say like 5, 3, and 1. Currently we have 3 different carets. And what we want to do is make it so we have 6 different types of carets. And in one move, we can split one caret into 2 different types of carets. For example, this 5 can become 1 and 4. That's not a 1. Can be 1 and 4. Can be 2 and 3, 3 and 2, or 4 and 1. They have to be like, each caret has to be positive size, and it has to be an integer, just like because. Otherwise, it would be annoying. So, and each caret has cost, like a caret of size x has cost x squared. And so we want to split these carrots such that starting with n, we have exactly k, and the cost of each carrot is at most, or the sum of costs of each carrot is minimized. Okay. At first glance, it's kind of like a greedy thing where you can like say split this into a 2 and 3, and then be done. And then like now you have 4 different carrots, and now you like take the biggest one and split that. But that just doesn't work, and here's why. Because sometimes you don't always want to split it into 2 at once. Say you have what would it be? Like 35. I don't know. Yeah, let's use odd numbers. So then this 35 would split into 17 and 18. But it could be better to instead do like 3 different splits at once, and then split this into an 11, a 12, and a 12. But that wouldn't work if you do it like this, because it only considers like splits that are kind of powers of 2, in a sense. But if you want to split to any non-power of 2, then you have a problem. Okay, now basically what we want to do is, we can think of the problem like this. We're going to assign each number a value x. And then we're going to split this caret into x different ones. So say we had 3 numbers, which I think is optimal. Then we would split this caret into 3 different carets, and we'll say that like, yeah, and then we'll split this caret into 2 different carets, and this one will be split into 1. And it's always optimal to like make these as close as possible, just because of like how x squared works. If you square a smaller number, it's better than squaring a bigger number. So we want to split them as evenly as possible to make every number as small as possible. And kind of like exchange arguments. Think about it like this. So you have x and x plus 1, and we can show that it's better than x minus 1 and like x plus 2, for example, by saying that this is like x squared plus x plus 1 squared, and then like you can do out the math and kind of expand it out, and it just works. It's better. I'm not going to do it because it's kind of a waste of time, but it's better. So now the problem is assigning these numbers. But this we can do greedily. The idea is, say we have this currently as a 3, and then what do we want to do? When do we want to change this to a 4, for example? When do we want to increase it? Well, what we can basically do is we can compute the cost of splitting. We can compute the total cost like we get at the end by splitting into 3, and then the total cost that we get at the end by splitting into 4. And then the benefit is we lose, say it's like f of, say f of n and x is like the minimum cost for a caret of size n into k, into like splitting a caret of size n into k separate smaller carets. Then the benefit we get from doing this transition is f of n3 minus f of n4. And so basically what we can do is we can just greedily take the change that gives us the most benefit. So in some sort of priority queue or something, we can say that, in some sort of priority queue, we can say that, we'll say that, like, for example, this caret gets benefit f of n3 minus f of, or it'd be like 5, f of 5 comma 3, and f of 5 comma 4. And then this caret would have benefit of f of 3 comma, 3 comma 2 minus f of 3 comma 3, and then this would have benefit f of 1 comma 1 minus f of 1 comma 2. Note that f is strictly decreasing by the same argument. We want to split it as evenly and as many times as possible. It's just like math, kind of. Get some intuition about squaring numbers, I guess. Don't really know how to do that, but I don't know, is this something people learn? I'm not really sure. I actually don't remember how I thought about this stuff. You can kind of do out some small cases, and then it just kind of makes sense that when you make numbers closer, they're better. So from here, basically, like, put all these in a priority queue, and then k minus n times, because that's the number of splits you need, take the biggest number out of this, like whatever the biggest number is, make the change, and then put the new cost back in the priority queue, and then it's just greedy from there. Yeah, and actually, there's some similar problem from Yusuko that I might link. That the full solution is actually harder and uses an even more advanced trick, but you can kind of apply this same trick to that problem. So you can see it as an exercise to kind of see how you would do the same thing as this to that problem, and I'll link it in the description. And I will note to myself now that I will link it in the description. And then, yeah, basically the trick is to compute like the best change you get and then do it like that. So now it just remains to calculate f. How do we do that? Well, basically optimal split is going to be like some number of floor n over x. Like this is going to be as even as possible. But some of these need to be the ceiling of n over x because like that's just how the number would work. So like for example, I'll do this out with a number. Say we have f of 10 and 3. The optimal split is 3, 3, and 4. So these two are the floor of 10 over 3, and this is the ceiling. So how do we figure out what these numbers are? Well, let's just say we set all of them to floor. And then we have n mod, oh, this should be x, by the way, my bad. Then we have n mod x remaining numbers. And so n mod x of these have to be 1 greater. So basically we have n minus n mod x of floor n over x, which is in this case 3, and we have n mod x of ceiling n over x, which is the same as floor n over x plus 1. No, not always, but no, actually, let's not do ceiling. It's yeah, this shouldn't be ceiling. This should be just this floor n over x plus 1. So this is the same thing. It's floor n over x plus 1. So because this is the optimal split, basically we have this many of these, and the cost of each of these is this squared. So it's just like this times this squared. And then the same thing for here, we have this many, we have n mod x of these, and so we just want to like square these. And then the cost is, therefore it's m minus n mod x times n over x squared, and then m mod x times n over x plus 1 squared. And yeah, that's how you compute f. And then the rest of it is just that. Okay. Have system tests finished? They have not. Okay, so everyone I didn't hack passed system tests, so it's good that, yeah. And where are we now? 87th? That's fine. That's still enough, which is just awesome. And good job, Anton, for getting 2700 maybe? That is cool. What did he do? Did he try? Huh. Okay, but so we have a very good delta right now. Yeah, awesome. Just absolutely awesome. Okay, this is F, the final problem I solved. I didn't make any headway on G or H, so let's just not go over those. Okay, so in F, basically it's like one of those like interval problems. So like the, what do they call it? The okay, let's say f of L, I'm going to capitalize L and R for a reason. F of L and R is the, say in this, it's the longest like contiguous group of ones in within this subinterval. Handwriting is OP. I'm gonna get a writing tablet eventually, just not right now. This is not an N, okay. Longest group of ones. And essentially we want to compute f of LR over all possible values of L and R. Okay. Now, in these types of problems where you want to compute like the value over everything or something, it helps to try and like fix something. Let's take the second sample, 1101001. It helps to fix something, and what that means is essentially like, let's say we fix the right endpoint, so we fix R. Right. So the answer is the sum of f. Let's say L equals 1 to n, and the sum of R equals L to n of f of LR. Basically, the sum of f of LR for all possible L and R, where L is less than or equal to R. That's the answer. And how do we figure that out? So let's fix the right point. And then furthermore, let's say we like compute it so these right points are kind of like also moving right. So what's useful about this? Well, it means that we already know the answer for this substring, for this substring, and for this substring. So let's just like consider this one, for example. Either it's the same answer that we already have here, or somehow this one plays into it. Because now we're computing this one. So if this one plays into it, then well, like the new substring that's better than the old one has to kind of be attached to this one. So we keep track of kind of the streak of ones we have that ends here. And in this case, it's just this. And then we say, well, okay, let's consider more general now. So say this is the right point we're computing, and let's do something like this. And this is the new point we added in. So immediately, this subarray has, this subarray benefits. Because the streak of ones over here just got extended by this. So everything in the streak of ones benefits, and specifically it gets one higher. Okay, now let's say the streak was of length k. We had k ones before, and now we're sticking on this extra one. Then that means that immediately we know that everything on this streak of ones gets added 1 to it. But also, everything to the right of it also has this streak of k ones. And the only difference this makes would be a streak of k plus 1 ones. So either like for any other endpoint, either it was already k or it's bigger than k. So either it's going to increase by 1 or stay the same. That is the observation. Either it increases by 1 or it increases by 0 when we stick on this character. Now, why is that useful? Because there's another observation we can make. That, consider like this interval, right? Well, it's just like bigger than this interval. And every group of ones we have in this interval is also in this one. So, for some x, for all x, let's use math notation, f of Lx is greater than or equal to f of L, capital L, L plus 1 x. Which means that as we go to the right, these are going to be like, it's like reverse sorted. It's going to be as we go to the right, it's going to be monotonic. It's either going to increase or stay the same. Which means that there's some interval where all the values are on here are less than or equal to k, and then all the values on here are greater than k. So So all the values on here are going to be unaffected because this new interval is of length k plus 1. So we can write this similarly as greater than or equal to k plus 1, which means that this isn't going to affect it. So the operation we do when we stick on this 1 is we find this interval where all values are less than or equal to k, and we add 1 to everything on this interval. Now this is this is sounding more and more like a segment tree, right? Because now we just need to add 1 on an interval. But how do we find the point where these values are less than or equal to k? Well, I mean, like we kind of just like spelled this out already. It's binary search. But like they don't really want you to do that, I think, because you have 5 times 10 to the 5th and you have 2 seconds, and it's kind of like n log squared n is not a nice constant. Let me just check this really quick. Awesome. This is so cool. Can we get IGM before the video ends? Will they update the ratings? Oh wait, this shouldn't be implies. That doesn't make sense mathematically, but whatever, it doesn't matter. So we have to add 1 on a segment tree, and now we have to find this point. So you can do it with binary search. If you're good enough at like constant optimization, you might be able to make that work. And the way it would work is you want the minimum on this interval to you want this minimum on this interval to be less than or equal to k, and then you want to find the leftmost. No, you want to find the rightmost point. So yeah, the rightmost point such that the minimum on the interval is greater than k, which you can do with binary search. But let's do better. Not only is f of Lx going to be monotonic, so not only are all of these going to be monotonic, but in fact the whole array is going to be monotonic. Because like we can just say that everything that we haven't computed yet is just 0. So we're going to have something like this. Let's just take some random numbers. For example, 3, 3, 2, 2, 2, 1, 1, 1, 0, 0, 0, 0, 0. And we want to find the point where we want to find some interval, not specifically this one, maybe this one, where everything on this interval is less than or equal to 2. And then finally, at the end, we would want to add 1 to this interval. And the way to do this is you would take some... Actually, no. So, like, here's the idea. You already have a segment tree. Like, you need the segment tree for the RMQ. So let's just make this faster, right? And the idea is you want to do the binary search inside the segment tree instead of doing a query every time. So here's the idea. You have a segment tree, and this L and this R covers 2 segments. Like this is the left side, and this is the right side of the segment tree. So we want to find the leftmost value, the rightmost value that's greater than k, right? Or we can similarly do the same thing as the leftmost value that's less than or equal to k. Let's do that. So we know that this is monotonic, and therefore if we have like RMQ, that's just not even gonna say we like each segment tree like represents the minimums. So because this is monotonic, this is greater than or equal to this. The left side is greater than or equal to the right side. So we can check if the minimum on this segment is less than or equal to k. Because if so, that means there's some number that's less than or equal to k on this segment. And so, therefore, we know that it's on this side. So let's go into this side. And if the minimum is greater than k, then we know that there's nothing on this segment, and therefore it has to be on this segment. So we would go into this side. Then we do the same thing for this. Either the minimum on either the minimum on the left is, let's say we're looking for 1, for example. Either the minimum on the left, which would be these, is less than or equal to 1, and then there's some element that's less than or equal to 1, or there's nothing, and therefore it has to be on the right. So now, this time there's nothing, so we go into the right, and then we recurse once again. And we see that this minimum is 2, so that doesn't work. So we have to go to the left, to the right. And then we have finally just something representing this and this. And once we do that, we see that there's a 1 on the right. So we go into the right, and now we found the point. And that's the basic idea. If that didn't exactly make sense, you can also check out my code. It's very, very simple to do this, actually. It's just this, where we, yeah. So you do lazy propagation for both positions, and then you ask if the mid is, the mid is this. So if the left is less than the value, then go into the left, or the minimum on the left, otherwise just go into the right. It's basically that simple, and the rest of it is just segment tree stuff. Okay, now we have this position. So let's finally return to the original problem where I've made such a mess of this string. So we're computing where this is the right point. And so we automatically assume we know what all these values are, and they're in the segment tree. So if this is a 0, then this doesn't, adding this character doesn't really affect anything. So specifically, the value of this is a 0, and the value of everything else remains the same. And so we can kind of just maintain this value. And otherwise, if it's a 1, then this possibly changes things. For example, we know this is a 1, so we have to change something. And then we basically compute, given that this is the right endpoint, the longest streak of ones we have. This is 2 pointers. If you understand the rest of this, you definitely understand 2 pointers. So that should speak for itself. You use 2 pointers here, and yeah. And then, so basically this is length k. We automatically know that everything on this interval gets increased by 1. And then we want to find the point using this binary search where everything to the right of it is at least k plus 1, and everything to the left is less than or equal to k. Or everything to the left is at least k plus 1, everything to the right is less than or equal to k. And then we add 1 on this segment. So you can do it with 2 segment trees, where the first segment tree does the RMQ that you need for this binary search, and the second represents the the sums. But you don't even need to do that, because you're going to take a sum of the prefix every time. So if you have a 0, say the sum of this prefix is r. So if you have a 0, then it's still r. And otherwise, so everything where this is the right point is still r, because it doesn't change anything. And otherwise, if it's a 1, then you just add 1 on a segment. And so it's basically r plus the length of the segment. So you can do it like this too, where you just maintain the sum as you go along. Either way, the answer is the sum of all this for all possible right points. Okay, that is A to F. And did I go over the hacks I did? I guess I could. I'll show you my hack case. This was, where was I? Yeah, my hack case was this. It was 1, 5. It was 1, 5, and this, and this. And so therefore, any solution that would check for, that would only declare that there isn't a cycle if there's something of this form, where the 2 things are not equal, then that would not work, because this you can't return from here because this blocks it off. But these solutions would conclude that there is a cycle, and therefore everything is returnable. But that's just wrong. So this was the hack I used. And if you failed system tests, that might also be the reason that there was some case like this in the system test, because there were way more system tests than pre-tests. Also, 2 people above me failed system tests, which is kind of surprising. But yeah, that's the idea. That it just kind of breaks their logic. Anyway, that was the round. I am obviously happy with how this went. I guess, yeah, that's just awesome. We got IGM. Tomorrow I'm doing Kickstart, which will be, like, I'll just release it after. And this Div 2 that's happening is, like, way too early. It's 5 a.m., so I might, we'll figure out something. Maybe I can cover it, maybe I just won't. And as for this Div 3, which is on a Tuesday, meaning I can't do it, I can stream it on Wednesday. And that's the plan for upcoming videos. And also, as I promised on my YouTube, which none of you probably read this, but when I get IGM, I'm gonna make a video about like how I got here, basically my journey to get to this point, and also what I did to practice and stuff like that. So that's gonna come soon. Look forward to it. I'll probably hype it on the community tab too. And if you haven't seen this, look at this. There's like some stream stuff going on here. And or join the Discord, and or do everything. You can click on this link and then it would take you to Discord. Yeah. Alright, that's all I have to say. Probably nobody's gonna get to this because it's at the end of the video, but yeah, that's it. Goodbye.